I'm going to talk about electric fields, and I'm going to use the analogy of gravitational fields. So when we had this force of gravity, and we had gm1 m2 over r squared, now we have this Coulomb's law, force of the electrostatic force is equal to kq1 q2 over r squared. So it's relating charges as opposed to masses. Well, when we had gravitational field, we have this mass. I'll just call it I'll call this m1, okay? And the field is this concept of, if I take a mass, a point mass, a test mass, and I put it in this field, test mass, terrible. And I put it in this field, so I'll have this little test mass there. What force will it experience? Okay, why do we use that? Well, one of the reasons we use that is because if I know the field at a certain area, I don't have to redo this equation over and over. Where have you seen that? You've seen that an awful lot right here at the Earth's surface. At the Earth's surface, we know that the force of gravity is m times g. And that g is the gravitational field strength. We didn't always call it that. Sometimes we call it acceleration due to gravity. But it's the gravitational field strength. It's how many newtons each kilogram of a test mass would experience at the Earth's surface. So if we put that test mass right there, I don't have to do this. I know that at the Earth's surface, 9.81 newtons per kilogram is the field strength. So I just take whatever the mass is, multiply it by the field strength. Thank God, because otherwise every time we had to find the force of gravity on something at the Earth's surface, we'd have to use this. We'd have to be punching 6.67 times 10 to the negative 11. Life's too short. Don't want to do that. So what we did is we said, this is the same thing as grouping this together. At this location, the r is the Earth's radius. Because again, that r is the distance between the centers of mass. Okay, so that's the Earth's radius squared. And you've got on top g and the mass of the Earth. And you plug those in and you get 9.81. So we don't have to keep redoing that every time we talk about something here at the Earth's surface. We just say the field strength is 9.81 newtons per kilogram. Hey, how many kilograms you got? Just multiply it by the field strength and you've got that. Similarly over here, the electrostatic field strength, instead of having to do, for example, if we have one big charge and we want to find out how it affects other charges near it, we don't want to have to keep plugging into that equation. So what we can do is, and I shouldn't group that, what we can do is call this the electric field strength. So now all I have to do is take a test charge. If I put it in that field, I know how strongly it's going to be attracted. It's going to be Q times the electric field strength. Q of the test charge times the electric field strength at that location. It's a little different from this, where we had this really useful one location where so much we live on the surface of the Earth. So of course, there's a logical place where we know the field strength. But you could figure out G anywhere. You could figure it out at the moon, at the moon's location. You absolutely could figure out G at the distance from the center of the Earth to a common orbital radius. But we're doing the exact same thing here. We are figuring out the field strength. That's the E field, electric field strength. And we're taking that field, multiply it by the charge at the location that we calculated that for, and we can find how strongly this test charge is going to be attracted to Fe. Now, what's kind of important when I say attracted It's really not quite that way, okay? If you look at this, we know that if I put a mass near another mass, they're attracted. It's a little more complicated with charges. So let me just put it this way. If I have a charge here, and I put another charge here, the direction of the field lines depends on what this is. Okay, so if this is a positive charge, then I put, and again, we're not really talking about signs here. If I put a positive test charge here, it's going to get repelled. Okay, so one of the things you need to understand, very, very important thing, is the field lines show direction a positive test charge would experience a force. Would experience a force. So in other words, we say to draw these field lines, we need to, excuse me, and get the lights back on. To draw the field lines, we need to say what direction would a positive charge experience a force. So if our central object, if our central charge is positive, all the field lines have to be out. Because if I put a positive charge there, it would experience a force in that direction. If I put a positive charge there, it would experience a force in that direction. So really drawing all my field lines, they would all be going out from a positive source charge. I'll call it a source charge or reference charge. Okay. Let me erase this. I've used that for my analogy. What if you had a negative charge here? What if you had a negative charge over here? What would the field lines look like? Well, if I put a positive test charge there, and that's what we're talking about, a positive test charge, it would experience a force in this direction. So the field lines always go in towards negative charges. So once again, these field lines are reference to this thing. It's basically saying what forces are going to be caused by this when you put something in there. So the field lines go in towards negatives, they go out towards positive. You can't have a field line coming out from a negative, because if I put a positive test charge there, it would get attracted. Okay? So we could have really, really complex field line maps. One that's called a dipole, we could have a positive and a negative. Okay? So we don't, now we're not even talking about just the Earth when we're talking about gravitation. We're talking about two planets, and I put a third thing in there. Where will it get pulled? Same sort of thing going on here. I don't expect you to be able to draw these perfectly, but we do know one thing. If I put a positive charge here, test charge here, it would get repelled by this, and it would get attracted by this. So there'd be a strong force in that direction. If I put a positive test charge there, same thing, it's going to get pulled in that direction. So there's going to definitely be a field line that looks like that. What if I put a positive charge there? It's going to get repelled. It's going to get attracted a little bit, but it's so much farther away that it's going to be almost straight out from there. And if we just go through, and if I just pick a whole bunch of dots and say, what would the fields look like there? This one is going to be mostly horizontal here. This one, it's going to have a component in that direction and a component in that direction, so that's going to be horizontal. And if we do that for every spot in the world, every spot around here, what we find is that the field lines for this dipole will end up looking like that and keeps all around like that. And you may have seen magnetic field lines that look like this. Works essentially the same way. Okay? Nice thing is this. If I have the map, and I say, hey, what if I put a test charge right here? positive test charge right there. These two are fixed in space. If I put a positive test charge in there, what force will it experience? Well, it'll experience a force in that direction. It just follows the field lines. So being able to take two or more charges and kind of figure out where the field line would work, that's one skill. Or taking a field map and being able to say what direction would a positive charge be pulled in that. We can just say, oh, what direction does the field line go? Okay. There's one variant on this, and not everything you put in there is going to be a positive, right? So the field lines show the direction that a positive charge would experience a force. If you put a negative in there, negative charge, I'll just pick right here. If I put a negative charge right there, it's going to be pulled in the opposite direction. So it will experience a force in that direction. Notice this is negative, of course. Well, negative is going to repel it, positive is going to attract it. And I didn't do the vectors for every one of this. This one would have a vector component in this direction. This one would have a smaller vector component in this direction. If I add them together, I should get that resultant, didn't draw it well, that resultant in that direction. Okay? So, given a field line, a set of field lines, and given a test charge, either positive or negative, you should be able to find the direction of the field. Excuse me, the direction of the force. And given the magnitude of the electric field at a certain location, and given the magnitude of the charge that you're putting in there, you should be able to find the magnitude of the electrostatic force. So that's how we use fields. Let's do a real quick one. If I have, let's just take this dipole situation, and let's just say right there, I know that the field strength is, I'm going to say, let's just say 100 newtons per coulomb. And if I ask, I'm going to put a 2 microcoulomb charge right there. Let's make it interesting. A negative 2 microcoulomb charge right there. What force would it experience? Well, first of all, this says, well, the force will be equal to Q, and we really only have to worry about the magnitudes of these things. 2 times 10 to the negative 6 times the E field, 100. Again, think of this like mass and gravitational field. 9.81, mass times G. Well, Q times E. And so you end up with 2 times 10 to the negative 4th newtons. This is newtons per coulomb. This is coulombs. We end up with 2 times 10 to the negative 4 newtons. Okay, so there's the magnitude, that we know how big that electrostatic force is. What direction is it? Well, this is negative. Remember, the field lines show the direction a positive charge would experience a force. So this will experience a force in that direction. And the force will be equal to 2 times 10 to the negative 4th newtons. So that's how we use electric fields. Electric fields cause charges to move. They exert forces, and those forces will make objects move. So electric fields are really behind everything that we use electricity for. When you flip a switch on, you've really created an electric field in the wires, and that causes charges to move in response to that. So what we've talked about charges, and we've talked about static electricity. We've talked about Coulomb's law, which is where we got this from. We've talked about the effect of electric fields, finding electrostatic or electromotive force. I should say electromotive force, electrostatic force. And next we're going to talk about charge motion in the static electricity world. In other words, not talking about current yet. And that'll allow us to get to the point where we actually see why charges move through circuits and how we can use that.